Hello everyone, and welcome to this online webinar for SCIA Engineer 15 versions. My name is Dominique, and I work as a customer service engineer for SCIA. The purpose of today's webinar is to give you a little bit more insight in our new functionality, general plasticity. Before we start, I will firstly give a short practical information about the GoToWebinar tool. Please make sure to check your sound settings. If you have any problems with the sound, you can check it here in this window. Next, if you have any questions during this webinar, please don't hesitate to insert them in the question box of your GoToWebinar window. We will try to answer these questions immediately after the end of the webinar. If this is not possible due to a lot of participants, meaning also a lot of questions, the answers on all the questions will be sent by email afterwards. And last, of course, this webinar will be recorded, so you can review it and watch it afterwards again, or on our website, scia.net, or on our official YouTube channel. Here you see the content of this webinar. We will start with some theory, so some introduction. First of all, which yield criterion is used or implemented into SCIA Engineer so far? And what about the used finite element model? Next, we're going to have a look on the general plasticity functionality and practice in SCIA Engineer itself. So first of all, what project settings are needed? What about material properties? And then we're going to have a look on some practical examples. We have 4 practical examples during this webinar. We have some walls, beam on 3 supports, base plate connection, column beam connection, and then we're going to end with a final conclusion. First of all, the introduction. So, general plasticity can be used on any 2D member in SCIA Engineer. There is no limitation, so you can use it on plates, walls, shells, so really any type. Second, 1D members are not supported yet for this functionality. So if you use the functionality general plasticity and you have in your project as well 2D elements as 1D elements, the plastic properties will be ignored for the 1D elements. To warn you, if you start the calculation, SCIA Engineer will give you a warning message about this so that you really know that 1D members are not yet supported. Of course, plastic behavior is nonlinear behavior, so it's needed to perform a nonlinear analysis. Really important to know is that this nonlinearity can be combined with other nonlinearities in your project. There are really no limitation on that except 2, meaning it is not possible to accumulate several types of nonlinearities on the same 2D member, of course. This, of course, would give some conflicts. First of all, for example, if you have a 2D member and you have defined it as being pressure only, and you have defined it as being existing of a plastic material, then the pressure only behavior will be ignored and the 2D member will just behave as a plastic member or plastic material. Second, if you have defined another 2D member, of course using plastic material properties, and you have defined it as being a membrane member, so with membrane behavior, in this case the plastic behavior will be ignored and the 2D member will behave as an elastic membrane. So this is really important to know. Okay, let's now have a look at the theory which is implemented so far into SCIA Engineer. The von Mises yield criterion is currently available. In future versions also some other yield criterions, an example is a Tresca yield criterion, will also be inserted into SCIA Engineer. So far the von Mises yield criterion is currently available. And this one is suitable for ductile materials in general, such as metals, being, for example, steel or aluminium. It is symmetric behavior, meaning acting in the same way in tension as in compression, with or without any hardening in the plastic branch. As mentioned before, more types of plastic behaviors will be added in future versions. Of course, prior to yield, material response is assumed to be elastic. That's logic, I think. In material science and engineering, the von Mises yield criterion can also be formulated in terms of the von Mises stress or equivalent tensile stress, sigma E. In this case, a material is set to start yielding when its von Mises stress reaches a critical value, all known as the yield strength sigma Y. The von Mises stress is used to predict yielding of materials under any loading condition from results of simple uniaxial tensile tests. On the right side, you see an image or picture of the von Mises yield curve and the Tresca yield curve. As mentioned before, Tresca yield curve will be implemented in future versions. So far, the von Mises yield curve has been implemented into SCIA Engineer. And you see here, this is a 3D dimensional stress diagram. On the bottom of the slide, of course, you can see the formulation of the von Mises comparison stress in a general 3D stress state, meaning that you have stresses, of course, in 3D or in 3 directions. If we go and have a look further on this von Mises yield criterion, of course, SCIA Engineer is a finite element software using 2D finite elements. So this von Mises stress formulation using the 3D or 3 direction stresses will be first of all recalculated into principal stresses, meaning that we only use sigma 1, sigma 2 and sigma 3, of course. And next, this will also be recalculated or reformulated into principal plane stresses, meaning that we only have 2 stress directions, sigma 1 and sigma 2, of course. And this one is the von Mises stress, how it is calculated in our software in SCIA Engineer. On the right side, we again see, let's say, the von Mises yield curve and the Tresca yield curve, but this time redefined it or redrawn it for a 2D environment. Now, what about the finite element model? As we all know, SCIA Engineer is a finite element software using finite elements to do the calculations. So how is this calculation done for general plasticity? First of all, drilling rotations at each node are used for in-plane loading. So this means that elements has 6 degrees of freedom at each node, and therefore it is compatible with other types of elements, meaning with beams or solid members, or doesn't matter which other type of elements. Within the element area itself, the Gauss 2x2 quadrature points are used. And each of these Gauss quadrature points is realized by 9 Gauss-Labator quadrature points throughout the thickness, as you can see on the images on the bottom of these slides. So the 4-node elements has actually 2 multiplied by 2, of course, multiplied by 9 quadrature points, so 36 quadrature points in total. Due to these Gauss-Labator points, these 36 Gauss-Labator points which are used, the element can handle bending loading with a very high accuracy. And, important, in all of these points, the nonlinear model will be computed independently using the plane stress formulation which we have seen on the bottom of the previous slide with sigma 1 minus sigma 1, sigma 2 plus sigma 2, of course, again. Okay, so far the theory. Let's now have a look on general plasticity and SCIA Engineer itself. I'm going to discuss some more slides in this PowerPoint, and then I'm going to show the practical examples live in SCIA Engineer itself. First of all, to be able to use this new feature or new functionality, you need the model ESAS.47. You can always contact your local salesperson for further information. Second thing, of course, your project settings or your project data. Since plastic behavior is nonlinear behavior, you need to make a nonlinear analysis to take this feature or this parameters into account. So you need to take on the functionality nonlinearity, and as a sub-functionality, of course, you need to take on general plasticity to be able to use it. Seems logic, of course. Okay, What about material properties? By default in SCIA Engineer, the materials will behave elastic. Now, this is an example you see on the right, the table on the right side of this slide is a table coming from Eurocode 315. So this is a table coming from the steel Eurocode, Eurocode 3. As you can clearly see, there are 4 different types of diagrams described here in this code. First of all, diagram A is a diagram which is elastic plastic stress strain diagram without any strain hardening. This you can clearly see in the diagram itself because there is a maximum value for the stress which equals the yield strength of that material Fy. Diagram B, stress strain diagram B, is also with yielding plateau, and if you can see here, this is an elastic plastic with a nominal plateau scope, which is defined by the number 1 in this diagram, and 1 is equal to the inverse of tangents of the E modulus divided by 10,000, or a similar small value. Next diagram, stress strain diagram C. This one is an elastic plastic with a linear strain hardening. And again, there is a certain angle defined. This time, this angle is described as being the inverse of tangents of the E modulus of that material divided by 100. Yeah. And the last one, diagram D. This one is a true stress strain curve, which can also be modified using test results. So you see number 1 is a true stress strain curve, and number 2 is a stress strain curve coming from test results. And of course then there are 2 simple formulas to calculate the true stress, sigma true, and the true strain. In SCIA Engineer itself, diagram A, B, and actually also C are implemented. D is not implemented in these versions. Now, to be able to use all these plastic properties, this plastic behavior in SCIA Engineer, of course, you need to define that in the material properties itself. And this can be done in the material library. So as you can see on this slide or in this picture, this print screen, in your steel material, this is an example for steel, you can choose the parameter material behavior for nonlinear analysis. So how will this material act during the nonlinear analysis? Of course, by default, it is just elastic. But now you can change it, the material behavior, into isotropic elasto-plastic von Mises. As mentioned before, for now, the von Mises criterion is implemented. In future versions, also other yield criterions will be implemented. And these are code independent, of course. Next, by the input type, I will immediately also show it live in SCIA Engineer. You can choose elasto-plastic with or without hardening. And if you have chosen for with hardening, then of course you can manually insert the hardening modulus, which is by default in SCIA Engineer, as you can see, the E modulus divided by 10,000. And of course you can insert the yield strength or the sigma y value as a limiting value for the stress, the von Mises stress. So, to continue on this material properties in SCIA Engineer, of course this is isotropic elasto-plastic von Mises as mentioned before. And you have 2 possibilities, without hardening and with hardening, which you can see in the stress strain diagram on the right side of this slide. Without hardening, of course, meaning that there is a maximum value for the stress, which equals the Fy value. If you have a hardening modulus, of course, then there is the stress can be higher than the yield strength Fy. And by default, the hardening modulus is E divided by 10,000. This is the default value in SCIA. You can change it manually if you want or need it. Of course, important is that we are now using isotropic elasto-plastic von Mises stress strain diagrams, but there is no limit for the strain value. So this means that what is implemented into SCIA Engineer, a diagram that is extrapolated. Since there is no limiting value for the strain, of course, you can use this calculation to calculate the plastic stresses. But of course, afterwards, you need to check the real strain values that has been calculated. And these values, of course, they should be smaller than a certain value. In, again, Eurocode 315, so this is again an example for steel, there is a maximum strain value given in this code for 5%. Of course, this is code dependent or even national annex dependent if you are using the Eurocode. But this is what SCIA Engineer is going to do. So first of all, we have a stress strain part which is in the elastic branch. Then we're going to the plastic branch, and the last defined segment of this plastic branch, this one is extrapolated to be able to continue the calculation if possible. But then you need to check the obtained strain values, of course. Okay, let's now have a look on some practical examples in SCIA Engineer itself. And the first practical example is called walls. So this is an example which exists of 3 identical walls, as you can see on the right side. Only the used material is different. And of course, in this example, the elasto-plastic von Mises without any hardening is used for material behavior for nonlinear analysis. I'm going to switch to SCIA Engineer itself. As you can see here, this is a really simple example containing of 3 walls with exactly the same thickness being 20 millimeters. Simply supported on the short edges with a fixed support, and also simply loaded with the same identical surface, vertical surface force on every wall. Next, of course, first of all, to be able to do the plastic calculation, I need to take on functionality, as mentioned before, nonlinearity and general plasticity, of course. Second, material properties. By default, material behavior for nonlinear analysis is set to elastic. Of course, in this example, I change it into isotropic elastic plastic von Mises. And the input type, you can choose between elasto-plastic, meaning without any hardening, or elasto-plastic with hardening. If you choose for with hardening, there will be an additional parameter here available where you can insert a hardening modulus, and you can insert here this yield strength, of course. As you can see, for every material, S235, S275, and S355, of course, the yield strength is inserted S355, 75, and so on. Okay. The only thing now that you need to do is to perform a nonlinear analysis, and of course make sure that every plate has the correct material. In this material properties, this is defined, so this will be used during the nonlinear analysis. And as you can see, first plate is with the yield strength or material 235, 275 for the second one, and 355 for the third one. I've already done the calculation, as you can see here. Linear calculation is done and nonlinear calculation is done, just to show the difference between elastic results and plastic results. This can be easily checked in the results menu under the option 2D members, member 2D stresses, of course. First of all, I'm going to start with the linear results, so I'm going to use my load case LC1 to show the results. Maybe some short explanation, of course. I will take on standard to be able to see some results in the color palette, but also the option section, because I have defined a section here, each time in the midsection of the wall, and also on the end section to be able to see some clear results. And I'm asking for the results, sigma E, which are the von Mises stresses. Plus means on the positive side of the wall, so on the positive local Z axis, and minus mean on the negative local Z axis. So the sigma E value, if I regenerate it, we see here the elastic result or the elastic stresses. As we can see, in the midsection, no problem at all. For the 3 walls, the calculated von Mises stresses are lower than the maximum yield strength, 190 each time. But on the end sections, I have 426.2 megapascal for the 3 walls. Of course, the results are exactly the same for the 3 different walls because the thickness is exactly the same and we are doing an elastic calculation so far. So as you can see, for each wall or for each material, the calculated form measure stresses are too high. So let's now have a look at the nonlinear combination or the results from the nonlinear combination. So this is now a plastic result taking into account the plastic material properties which are defined in our material library. If I regenerate it, and we can clearly see the difference now in the results. First of all, of course, the results or the stresses are distributed now in a different way. In the midsection, they have become slightly higher than with the elastic stresses, but on the end sections where the stresses were too high for the elastic results or the elastic stresses, they are now clearly a lot lower, and as you can see, each time they are more or less exactly the same on the used or the maximum yield strength. 234.8 for our material S235, 274.7 for our material S275, and 353 for our material S355. So each time exactly or more or less exactly the same value as my yield strength. And important, of course, they are never higher than the maximum yield strength. So this is now the plastic result, which is done during the nonlinear analysis. Okay, so far the stresses, but now of course we need also to check the calculated strains because they have to be lower than the limit value defined in the code or in the national annex, depending on which code you are using, of course. And in this version of SCIA, this can be done by 3D stresses. In future versions, this will be available also here in this menu, member 2D, that will be named stress/strains. But for now, I'm going to check it in the 3D stress values. Of course, I'm going to start only with the nonlinear results, so the plastic results, of course. I'm not going to discuss the linear results anymore so far. Here the same thing. I can ask here for principal magnitudes and I can ask for sigma E. So this is exactly the same as in the other menu. You can see here the results which are exactly the same within this 2D member stress menu. But what I'm interested in here are the strains, of course. And of course also only the strains in the principal directions. I'm going to start with principal total strain. And I'm going to select, of course, epsilon total M, M standing for Mises again. Now, this is a result of elastic strains plus plastic strains. And that is also the reason, of course, why you see some results for the strains here in the middle of your plate, even though that there was no need to reduce the plastic stresses there. As you can see now, we clearly see that the highest strain values are of course there on the end sections of the walls where our stresses were also of the highest value. And we see that the maximum value of this elastic plus plastic strain is now 0.44%. What we're interested in, of course, is our plastic strain value, so that we can choose principal plastic strain and we choose for the value epsilon plastic M. I regenerate this result. First, what we can notice is that in the middle of these walls, of course, the plastic strain value is equal to 0 because there we only had our elastic strains. And there where we had this plastic region, again on the end section, there we have a maximum plastic strain value of 0.33%, as you can see in here, which is again much lower than the 5% limiting force. So okay, so far so good, because our maximum stress was lower than the F yield, or the Fy value, and our maximum strain value is also lower than the limiting value of 5%. This is also again shown on a few slides in this PowerPoint. So here we see first the result for our elastic stresses, not taking into account the plastic material behavior. And now you see that again on the end sections we have a stress value, a von Mises value, which is really too high, 426.2 megapascal. Next we do the nonlinear calculation, taking into account the plastic material behavior. And then we see that nicely, our maximum yield value is taken into account, so we receive each time a meter stress which is lower than the maximum yield value. Next thing, of course, okay, this is clear, but then we need to check our stresses. And you have the possibility to check the total strains in the SCIA, so the elastic and the plastic ones, which you can see in here, 0.44%. But of course, what is the most important one are our plastic strains. And these should be lower than 5% that we find in limiting code, undercode, or international annex. And you see here in the end section, we have a maximum value of 0.33%, which is much lower than 5%. So, okay. Let's now have a look on the second practical example. This example is actually a beam on 3 supports. You can perfectly model it really fast with 1D elements. In this example, it is modeled with 2D elements using plates and walls to be able to use the functionality general plasticity, of course. And again, I'm going to switch to SCIA Engineer itself for this example. First of all, of course, the material properties that are used is again isotropic elasto-plastic phomesis without any hardening, but the yield strength here is reduced. So I have used a material S235, but in some codes, the partial safety factor gamma M0 is equal to 1.1. So that's also the reason why I have reduced this maximum yield strength, because 235 divided by 1.1 is perfectly equal to 213.6. As you see it here in this value. We can do the same, we can check the results. I'm quickly going to put out the rendering. And I can do the same. First of all, linear results. Sigma E values. I have a really high stress value of 600, let's say 680 megapascal. And of course, it will be here in the midsection where I have this intermediate support. If I check the same result now for my non-linear calculation, so taking into account the plastic material properties, you directly or immediately see changements. Of course, the maximum value is now 213.6 because that is the maximum yield strength which is inserted into the plastic material properties. And you see now a big range or a big area where your plates and walls are going to start, or your material is going to start yielding. Next, of course, the next thing is that we need to check the stresses. So in this case, I'm going directly to our nonlinear combination to check the plastic stresses. And I'm going to choose for the principal plastic strain, again, epsilon plastic M. If I regenerate this result, we see that for only mostly of the entire beam is equal to 0, so there is no plastic strain. Only in this small region, again where the beam is supported, there you have the maximum plastic strain value, which is now really too high, which is 62.12%. This is also mentioned in 3 slides in this PowerPoint. So first of all, elastic stress, as you can see in the midsection, is let's say 680 megapascal. Plastic stress during the nonlinear calculation is of course reduced to a maximum value of 213.6. Again, keep in mind, this is just to show you the principle Fy divided by gamma M0, which is in this example equal to 1.1. And this results into a plastic stress which is really too high, 62%, which is much higher than the 5% limiting value in the code, so this is not okay. Our next practical example is a steel base plate connection. Of course, we have in SCIA Engineer and in design forms 1D solutions for 1D steel connections according to the Eurocode 318, or according to the American code. For steel connections, 1D steel connection according to those codes, I refer to a previously given webinar which you can find on our website or on our YouTube channel. Now, if you have a steel connection which is not described in that certain code, you can always use general plasticity or finite elements to check that steel connection, of course. In this example, A simple base plate connection is modeled using finite elements, and of course general plasticity is used. I'm going to switch again to SCIA Engineer. First of all, something about the model. This is a simple base plate connection, as you can see, where the bolts are simulated with these nodal supports, which are described as being rigid tension only. Rigid tension only is also a nonlinearity, which will be combined with the other nonlinear parameters as being plastic behavior of your steel materials. The base plate, or the base plate connection, let's say, is loaded. First of all with a vertical surface force, and of course with a horizontal force to have a moment in your base plate connection. Next, the column itself is modeled with 3 walls consisting of the material S355, and the base plate is modeled as a plate consisting of the material S275. About these material properties, I'll show you the used ones. I inserted some bit more security or safety in this project. So as you can see, material S275 inserted a maximal yield strength for plastic behavior during the nonlinear analysis of 265. Same for material S355. Additional safety of a value of 10 megapascal using a yield strength 45 megapascal as a maximum value. Now let's have a look on the results. So quickly de-render. Let's start with member 2D stresses, and of course, like always, the linear results for sigma E, or the elastic results, I must say, for the von Mises. As you can see, a maximum value of 635.8 megapascal, which is of course really too high, and located as expected in this region, because we have bending moments which will act in this direction. If we check the same for the nonlinear combination, taking into account the plastic behavior of that material, we see now we have a reduction with a maximum value for sigma E, or the von Mises stress, of 343.6 megapascal, and of course again in this region. Now the only thing we need to do is check the strains for this nonlinear combination, and of course I'm going to ask again for my principal plastic strain alpha plastic M. We generate it, and two things now. First of all, you see that now also there is some sort of deformation shown. There's one simple reason for it. The deformed structure menu here is ticked on. Second thing, we see now that we have our maximum strains value, maximum plastic strain value, which is equal to 0.25%. So again, this passes. Next thing I'm going to do is select only the column to see where are these plastic strain values the highest, and of course there are here these 2 points where we have the highest plastic strain values. So again, this example passes because our stresses are lower than the yield, von Mises yield stress, and of course our plastic strains are lower than 5%, the 0.25%. This is also shown in a few slides in this PowerPoint. So first of all, our base plate connection with the nonlinear plastic behavior. Next, we had our elastic stresses, which were really too high, 635 megapascal. But if we then perform the nonlinear calculation, taking into account the plastic material properties, then we see that now our plastic stresses are lower than the Fy value with a maximum one of 243.6 megapascal. And important, of course, because we mainly need to check the plastic strains now. These are the highest ones are equal to 0.25 or 0.26%, which is again much lower than the 5% limiting one. So okay, this one passes the stress strain check.
The last example of this webinar is again a steel connection. And of course we used our nonlinear behavior for the material isotropic elasto-plastic von Mises with a limiting yield strength of 235. Let's now first have a look about how you can model this type of bolted column beam connections in SCIA Engineer using 2D finite elements. Of course, first of all, we start with modeling the column and the beam itself, and this you can simply do using 2D finite elements, plates and walls with the correct nonlinear material assigned to it as 235, of course. The next thing is insert the bolt openings in the column flange. This is also simply done using the structure menu, 2D member components, and then of course using the option opening. The next part is modeling the connection elements itself, of course, meaning the end plate of the connection and the haunch, again using simple 2D finite elements with the correct steel material and inserting some openings in the end plate for the connection. The next part, or the next thing, and the most important part of course, is make sure that these two elements are connected. I mean the flange of the column must be connected or has to be connected with the end plate of the connection, of course. And for this we use the so-called dummy elements or dummy beams. First thing that we want is to assign or to model enough dummy beams so that we have a sufficient connection between the end plate and the column flange. Next thing, these beams, of course, we will not want to add additional weight to the structure, so we create a new material. And this material we use a lower unit mass, we use a very low value of 1 kilogram per cubic meter. And we higher the E-modulus so that we will have a more rigid material or more stiff material to have a rigid connection in between the two elements.
The next thing, when we have created this dummy material, we assign it to the beams or to the connection elements. Connection elements will be modeled as being beams, and we give them the beam nonlinearity parameter press only, so that this one will be taken into account during the nonlinear calculation, that no tension forces will be there in the connection elements.
Next thing is the bolts, because now we have inserted all our connection, we have connected the column flange with the end plate, but still we have to model our bolts, and for this we can use a simple cross section as you see in here, RD12 we have chosen, with the correct steel material of course. And again, what is now important is that these bolts, or these beams as we use them, will be connected to the edges of the opening we have inserted in the column flange as well as in the end plates. And for that again we use our created dummy material and our dummy beams, which we will give the press only beam nonlinearity. Okay, let's now have a look again in SCIA Engineer.
The structure is loaded with one simple service load, as you see in here, and this service load I will take into account for these different nonlinear combinations to have different loads on the structure to put this steel connection to its limits. Now, if we have a look on the results, because that's what we are interested in, of course, and I'm going to de-render. First of all, I have created, quickly show it, multiple nonlinear combinations. So load case 1 is the self weight of the structure, and load case 2 was a surface load that I have inserted here on the beam flange, which will result in, if we recalculate it, into a line force of -3 kN per meter. Second combination -15, -20, -25, and so on. So everything is recalculated to have a clear line force. If we now have a look at the result, and we're going to have a look at the stresses for the first combination, of course, the lowest force, then we see we have some small stress values of 87 megapascal. So here is no issue at all, and there is no need to reduce the maximum yield strength or the maximum von Mises stresses. Maybe also show you the materials that is used. This one is a dummy material that is used for, let's say, the bolts, the beams, and the connection beams between the end plate of the connection and the column flange. And this one is again just a plastic material that is used material behavior isotropic elasto-plastic with a limiting yield strength of 235 megapascal. If we're going to have a look at nonlinear combination 2, which will result in line forces minus 15 kilonewton per meter, then we now see that we reach the value of 235 megapascal. So this elastic stress should or would be higher than this limiting yield strength. So we immediately see, okay, these are the points where of course the stress are the highest. In this location and of course in this compression zone. If we go further on with the next nonlinear combination, we will see that the region in which the yielding appears or on which the von Mises stress reaches the 235 limit value, of course, will be much bigger. And if we continue with a higher force, then of course this will be even bigger and bigger and bigger. Now you also see here this location of course, and also here in the midsection. But okay, still the case that the von Mises stresses are lower than 235 megapascal. This is always the case because we are calculating it with plastic material properties. But if we now check the strains, I'm going to start with my first nonlinear combination again for the plastic strains. Then of course we see that we have a constant value equal to 0. All the 2D elements are colored in green. Constant value equal to 0 because we had our stresses were equal to 80 megapascal or 87 megapascal, so no plastic strains at all. If we look at our second nonlinear combination, then we see that we have some plastic strains of course now, mostly again colored in purple, so again constant value of 0, but we have here in this region and of course here in this compression region some small area where we have some plastic strains with a value equal to 0.12 or 0.13 percentage. Then we continue our next nonlinear combination. Then we can clearly see that the region where the plastic strain is a little bit bigger, and the value of the plastic strain, the maximum value, has also a bit higher, now 0.4%. And so we can continue. The next nonlinear combination, again a higher value of the plastic strains, and of course a value now equal to 1.11%. So still okay, still passes the check. And we see now, we can clearly see that the maximum strains are located here, again in the compression region and tension region of this connection. If we have a look at the results again in our PowerPoint. So first of all, this PowerPoint, the results for the maximal load or the highest load is shown. So for the last nonlinear combination, and here we see that our elastic stress was equal to 626 megapascal, so really too high. So if we perform the nonlinear calculation, taking into account the plastic material behavior, then we see that we have a plastic stress of course equal to 235 megapascal. But again important, we need to check the maximum strains. And here the maximum strains are now 1.11%, which is again lower than the 5%. So okay, also this steel connection passes the stress strain check. Okay, so the final conclusion for this webinar. First of all, this functionality, general plasticity, can be used for all types of 2D elements in SCIA Engineer. So it is possible to use it for walls, plates, shells, and so on. The implemented yield criterion so far is the von Mises yield criterion. This one you can choose in the material properties in your material library in SCIA Engineer, and here you can define whether you want to use this von Mises yield criterion with or without any hardening modulus, and what is the yield strength of the used material. Important, of course, is that you need to perform a nonlinear analysis to take this general plasticity into account, and that this can be combined with other nonlinearities in the project, such as support nonlinearities or beam nonlinearities and so on. Important one is that there is no limit for strains in SCIA Engineer. Remember the fact that the stress strain diagram will be extrapolated so that there is really no limit for the strains. That is the reason why you could check easily in the results menu in SCIA Engineer the calculated plastic total strains. Okay, this is the end of this webinar about general plasticity, new functionality in SCIA Engineer 15 versions. Thank you for attending this webinar. If you have any questions, please don't hesitate to insert them in the question box of your GoToWebinar window. We will try to answer these questions as soon as possible. Maybe also good to mention is that there are several webinars coming in the future. First one is a seismic analysis. We also have one about civil structures, and we have a webinar coming about the engineering report. If you have any questions, please don't hesitate to contact your local sales representative or email sales@scia.net. If you have any user questions, it's best to send an email to support@scia.net. Thank you for attending this webinar.